but you do wish to do what will actually help.
Yeah.
And for my opinion, it's the best. And I can't do it from the day one because specifically in calculus, in linear, it's a bit easier. But in calculus, it took some time to be able to solve questions. But when I finish series, I think today even, then you are able to solve all the question with the series. And the number 5 question from engineering, which is the monotonic sequences, that's 2 questions of the test. Third one is limits, which is the easiest. The only reason that I'm keeping it less, I told you, it's because of L'Hopital rule, because we didn't learn it yet. But these are 3 questions out of 5. The other 2 are more, I don't know, theoretical, right? So you have to study for them. But yeah, okay. So I've started the recording, but I didn't share my screen. And I started with saying that Tuesday at 11 we have office hours at my office. Everyone are invited, and if it will be helpful, then we'll have more of it in the future.
Having 5 hours of math, you say we'll have
7 hours. When you say like that, who can resist? Okay. I'm seeing a mail from Hag.
I talked to Nir because like going to his classes on Thursdays at 4 to 8 is like very hard like to arrive. So like I was talking to him if there's a way to change them. He was like probably not. I think that doesn't have the open hours to do.
Well, so that's raises this question in Tuesday. We'll take it. Sorry. Okay. Well, the rest of that, the first one, calculus or. So we're back to calculus. We've learned about series, and we said as such, a positive series has 5 Spock's tests to make sure if it's converging or not. And any series, if it's absolutely convergent, meaning when you take the absolute value, if it converges, then it's also regularly converging without the absolute value. So we had some focus about the positive series, but then we will speak today about a couple of tests for a convergence of general series, not just positive ones. But we finished with the condensation test, and I need to give you an important example for it. And then we'll move on to general series. And yeah, and it's even written here. The generalized and harmonic series theorem. And the generalized harmonic series, or with it says some delay. Slight. I'll write it in if you want 60, then
How many tabs do you have?
how many times what?
How many tabs do you have?
No, it's on my computer. No, it's on my computer.
It's the
And
connection.
it's the connection, yeah. No, on my computer I see it perfectly, but yeah. No. Oh, it's pretty, it's a few, I don't know, few good seconds behind. And let me think if I can do anything about it.
Sometimes the university Wi-Fi just.
Well, yeah, okay.
Connected to it by Wi-Fi.
And
No, it's
I'm connected by the Wi-Fi. This is connected by whoever knows. Yeah. Well, just a second. I'll connect my HDMI cable, and then you'll see what I see. And my computer is not a problem here. On this side, anyway. and I try to keep my tasks organized. I have 2 children. I try to get order when I can, where I can. Audio, video. Second, sorry. By the way, now we get our point. Fine, I think now we're done with the technical issues for today. So theorem, the generalized harmonic series, sometimes called P series. And the series sigma from n equals 1 to infinity of 1 over n to the p OP is converging if and only if p is larger than 1. Okay, so when p equals 1, it's the actual harmonic series. And we prove that when p equals 2, it converges. But now we're doing something much more general. Whenever p is larger than 1, then it's converging. Whenever p is 1 or less, it's diverging. And what's the noise? I think it's from this, whatever. We'll live with it. And it's important to know that p doesn't have to be a whole number, a natural number, or whatever. It's a real number. Okay. And so let's prove that theorem. And it's very important because we learn about 2 comparison tests. We usually compare any series to a p series, right? We check whether the limit of the ratio between our series in the question and 1 over n squared is finite or not, and that's the way we answer some of these questions. Okay, so let's prove the theorem. It's an easy proof. It's between a theorem and an example, because we'll almost just do the condensation test. Only one thing we need to do, if p is smaller or equal to 0, then n over np does not tend to 0, and therefore the series diverge. Okay. Why did I separate the positive p's from the rest? Because for the rest, now if p is larger than 0, then 1 over np is monotonic decreasing. And that's what I need, that's the assumption I need to do the condensation test. So if P is negative, it's not actually decreasing, it's increasing. But in any case, the theories diverge, not a hard thing to do. When P is positive, then the question actually starts. Try to think about it. Imagine if P is -1, for example. So what is 1 over n to the power of -1? It's just n. Obviously, it's diverging, right? But I can't say it's decreasing and use the condensation test. So I must separate it into two cases, but the first one is completely uninteresting. The main thing is to separate between the square root of n and n in the power of 2. Why does one converge and the other one diverge? We'll see in a bit, okay? Actually, one last thing that I will say by heart, if P is smaller than 1, then obviously it's divergent because it's bigger than the harmonic series, which we proved to be divergent. And if P is larger than 2, then it's converging because it's smaller than 1 over n squared. But what about n in the power of 1/2, 1.5, for example? Luckily, our proof will be much more elegant and fast, so I won't have to do these cases, but in my mind, smaller than 1 over n, sorry, bigger than 1 over n is obviously diverging, and smaller than 1 over n squared is obviously converging, but in any case, we'll see it all together. Yes, sir. Yeah, okay. Yes, Thomas.
I mean, I wasn't in class, but I saw the recording one year from 1 week ago. And if they proved it for P is 2 or bigger, it's because it's
once you have 2, then everything bigger works, because if you raise the power of n, because it's in the denominator, you decrease the series, and then it's just the first comparison test.
Okay.
That's exactly what I said, but I don't use it now. That's why I said it and didn't write it. I will use the condensation test, and it will give us the final claim that when P bigger than 1, it's converging, and when it's between 0 and 1, it's diverging. And lower than 0, obviously diverging. And we can use the condensation test. So what does the condensation test says? It says that the original series is BFF with sigma from n equals 1 to infinity of, so 2 to the n always times 1 over 2 to the n in the power of p. Agreed? That's the condensation test. You multiply by 2 to the n, and you do composition. You replace n with 2 to the n. Agreed? But this is a geometric series, because that's actually equals to, so it's 1 over, no, not even 1 over, 2 to the power of n minus np. Agreed? 2 to the n here, that's 2 to the power of n times p, and a fraction is a subtraction in the power. And that is equal to is 1 to infinity of 2 to the power of 1 minus p to the power of n. Agreed? Yes, no? So this is a geometric series. This is a geometric geometric series which converge if and only if the Q, the ratio 2 to the power of 1 minus p is smaller than 1. Agreed? And when does 2 to the power of 1 minus p smaller than 1? If 1 minus p is negative. Agreed? You need the power to be negative, not p is negative. You need the power, right? 2 to the 0, since 2 to the 0, it's 2 to the 0 is 1. So if you go below it, you get something smaller than 1, and if you go above it, you get something bigger than 1. And if p is, if it's exactly 2 to the 0, it's also divergent because it's equal to 1. QED. Because 1 minus p is smaller than 0 means p bigger than 1. That's exactly what we claim. So it's very elegant. It's the main reason for the condensation test. The two common examples are this and the log that we did last time. Yes. Think about it. It's hard because you see this expression, but if it was 3 to the power of n, do you agree it's absolutely divergent? 3 to the power n going to infinity, right? And if it was a third to the power of n, and we proved that the geometric series, we calculate it, and we even know where does it converge to. It's x over 1 minus x. It's a fact, but it makes sense. Half to the n is the easiest, right? Because what's half plus 4 plus 1 over 8? That's a 1, right? So that helps you remember. But we prove it. We calculate. It was the first thing, I think the very first thing we did with series. If not with the very first one amongst the first. But let me look for it. Yeah, the geometric sum. Let me see if it was the very first. Yeah, these were just, I don't know, examples, and then the geometric, and we proved that if x, the constant, is smaller than 1, then the sum converges, and this is its sum. And this starts from n equals 0, not n equals 1, but it doesn't matter at all. It doesn't matter. It changes the sum. It doesn't change in the very fact that it's convergent. Okay. So, any questions so far? So, next, now we learn about general series, meaning not only positive elements. The sign changes from time and time again. So the first test is the Dirichlet test. I'm not sure how to write it. Dirichlet. Okay. Speak it. Right here. Okay. Dirichlet test. Given a monotonic decreasing sequence an such that an tends to 0, up until now Next. Up until now, it's still positive. Because if an is decreasing and tends to zero, that means that it's a sequence of positive numbers going to zero. That's the positive part. We'll have a second part. And given a sequence Bn such that its partial sums sequence is bounded, meaning the sum from 1 to any number, did that work? And I don't know, any k whatsoever of the Bn is always smaller than m for all k. Okay, so I will already say that the main confusion for students here is thinking that Bn must be bounded, not Bn should be bounded. It's sum. Take for example, well, I'll finish the theorem and then I'll give you an example. The theorem is near its end. Then the sequence from n equal 1 to infinity of a and bn converge. Okay, that's the theorem. So I'll let you finish writing it in your notes, and then I will give you an example that will explain why is it usually a general series, not a positive series.
I mean, Bn can be divergent and
No, but why it makes sense that Bn will change sign? Because An does not change sign. But I'm saying if Bn does not change sign, that if Bn is only positive, I will say that and I won't write it. Now I see that I wrote this wrong. It made the series, okay, about just a second, sorry. Sum from n equals 1 to k of Bn. So if Bn was only positive, the fact that its partial sum sequence is bounded means it's increasing and bounded, that's for it converges. Multiplying by a number that goes to 0 makes it even smaller, and then by comparison test we are done. It shouldn't even be a test. It's only interesting when Bn does not have the same sign, when it changes sign, and that's the reason that becomes bounded, and I will show you in a second. 3 examples. I'm not showing you how to use the test, but some things about it. If Bn is actually the fixed element 1, the fixed sequence 1, then its partial sum sequence, what will it be? It will be n, right? Because you sum up the first n numbers, which are 1, that's n. And it tends to infinity. And is unbounded since it tends to infinity. If Bn is -1 to the power of n, then its partial sum sequence, what will it be?
1.
Exactly. It's depends if we start with 0, 1, but it doesn't really matter. The Sn is -1 0, -1, 0, and so forth. Agreed? Because each time I add the next one, and is bounded. You see, the reason that it was bounded is because the elements were eating at each other's heels, right? One tried to grow, the other one said, no, you're not, right? And that behavior comes naturally from changing signs, right? One's positive, one's negative, and it doesn't have to be once, right? It could be 3 positive numbers, then 10 negative numbers, whatever. But every time you need to reverse the sign in order not to be unbounded, unless you have, and if you have the same sign always, then that's a converging series and you don't need a test. An interesting example is if Vn is sine of n. What do you say about that? Is that bounded? Why?
Each cycle.
No, but it's radians. So you never do a cycle. If it was in degrees, then yes. Then after 360, you'll get back to the first step. By the way, even then, it's not completely clear because the sum, you need to prove that it's 0. I think it's true, but in any case, it's not our case. N is in radians, so sine 1 plus sine 2, it's not clear at all which numbers are these. But that's the main thing. Like I said, the mistake students usually do the confusion and say, oh, sine, obviously it's bounded. But I'm not asking whether sine is bounded. I'm asking whether the sum of the first n sines, or the sign of the first n natural numbers, is bounded. It's not clear at all, right? Because each sign by itself is at most 1. So it's no more than n, but n is unbounded, right? That's a very interesting example that I will solve in a bit, okay? We will show that the sequence above is bounded, but if we take it in absolute values for absolute convergence, that is unbounded. Is unbounded. And it's not clear at all, but we will see these things in a few. Yes, Sammy, yes. It's like the main thing in our subject. It's the sum of the first n numbers, right? That's the way we define a series. If you wish to sum sine of n to infinity, then you will sum sine 1 plus sine 2 plus sine n. So if you stop at n, that's the n element of the partial sum sequence. Yes. Yes. And the definition of a series is the limit of Sn. Yes. It doesn't matter. I just changed the name to speak about partial sum of. Yeah. It's the partial sum, which is the partial sum, which is the partial sum sequence of the sum of absolute values of finite. It will be clear what I'm talking about, why am I talking about it in the future. But like I said, we will wish to speak about absolute convergence of a series, and you won't be able to use the Dirichlet test because the partial sum sequence there is unbounded, therefore the test does not hold, the assumptions don't hold. Yes, Thomas.
When you were talking about this, I was thinking about in our homework about -1 to the n+1 times n+1/2n. Is this not interesting because it tends to 0, or is it also one case where you could?
No, it does, and I'll open the tests again. We spoke about it last time. We say it looks similar, and then I told you we make all tests look similar. By which I mean you see -1 here. Well, you see -1 here, and you see -1 there, right? So you might be tempted to say, so it must be the Dirichlet or Leibniz rule. Leibniz rule is a specific example of the Dirichlet with -1 to the end. In any case, it might be, but it might be absolutely converging. And when you check the absolute converging, you put the absolute values and the -1 vanishes, right?
Yeah.
So you don't know ahead whether you will need the Dirichlet or Leibniz test or not. But yeah, if it wasn't absolutely converging, then you usually go to the Dirichlet test. That's the next step, as we will see. And again, these type of question from the test. Question number 2, you will be able to solve today. Question number 3, you're supposed to. And question number 3, you're supposed to be able to solve from a long time ago. And I will urge you to actually do it, right? It will prepare you to the test. And it will raise question if you say, oh, we have no idea what's going on, and then we'll do more office hours and make sure that you do. Okay, the lecture and the TA is rather general up until now. Now we are at the point of the course that you can start studying for the test, and you should. Okay. Sammy, you're.
This thinking it's in a month and a half. I think when I think of
That's not right. Well, 2 weeks it's more than you need. You can study like in 2 minutes for this test, no? Yes.
Wait, what are you saying?
Here another question like that.
It's 3 weeks.
But you shouldn't start studying from the end of the semester.
I don't think.
That's a fallacy. You do. Why? What do you mean you don't have time?
I literally don't, I don't really have that much time.
So that's a mistake.
It's like 20% of my brain.
I don't think it's 20%. There is a quiz, it's maybe 10%. But still, 80 is more than 20. You need to study for the test. That's more important by far. Don't have time. How many courses do you take this semester?
It has 40 hours.
So if I don't read computer science.
No, that I agree. No,
That's what I'm talking about.
yes.
Computer science
No,
is-
yeah. Yeah.
I literally won't know how to
No.
do it.
I agree that computer science homework, that's the real problem. But in my course, if the homework will make you fail the test, it will be incredibly stupid. Oh, yeah. But still, you can find a couple of hours a week to try solving things for the test while you have the lecturer willing to help you understand something. That's the reasonable thing to do.
Before we.
Since you're a student, you'll probably not do the reasonable thing, but I'm still putting it out there. It's nothing personal. It's not even because you're international. It's all students of all times, everywhere. Yeah. At the same time, yeah, it's like spreading your students. You're both failed and not failed until you open the grade. Yes. But it's okay. Yes. Okay. But you need to do it. Okay. Now let's do a quick example. That was 3 examples. Now we can do an example. Example. First one, it always has to be the same one. The sum from n to 1 to infinity of -1 over to the power of n over n. So here, an is the sequence 1 over n, which monotonically, well, whatever, decrease to 0. And the partial sum sequence of -1 to the power of n is bounded. Therefore, that series converge. That's it. Okay. We have a multiplication here, a product of 2 sequences. 1 over n and -1 to the power of n. That's exactly the an and bn from the theorem. What?
The sequence of the sum.
I'm not sure what I said. Right? Again, I'm going back to the theorem. The theorem says, if you have a series of a product of 2 sequences, one of which is monotonically tending to 0, and the other one has a bounded partial sum sequence, then the series converge. That's the theorem, and that's the way we used it. We said that -1 to the power of n over n is a multiplication of 1 over n, which decreases and tends to 0, and -1 to the power of n, which has a bounded partial sum sequence. Therefore, this series converge. Does it absolutely converge? Does it absolutely converge? No, since the series of absolute values is the diverging harmonic series, right? The sum of n equals 1 to infinity of the absolute values of -1 to the n over n is actually just the harmonic series. So what do we say about the state of this series? This series is conditionally converging. Conditionally converging, meaning it's converging, but not absolutely converging. Agreed? That's what I said. We're converging, but not absolutely converging. That's the way we call it. No. But that could be also with absolute converging. The very definition of conditionally converging is that it's converging and not absolutely converging. That's what we call conditionally converging. Because you could take a sequence with negative and positive series with negative and positive elements, which absolutely converges.
Yeah, but I mean that you can, I mean, yeah, of course.
No, I didn't just jump your throat there, because sometimes students make the mistakes and they see the -1 and say, oh, then it must be conditionally because I see the negative numbers. No, it doesn't mean at all, right? You have to make sure that the absolute value does not converge in order to call it conditionally. And that's like a question on the test. You need to make sure. The steps and to decide whether all right, whether a series absolutely converge, conditionally converge, or diverge are as such. Step 0, if the sequence AN does not tend to 0, then the sequence, the series, sorry, AN diverge. It doesn't happen often, but it does happen enough once in a test for you to need to know that. Mostly AN tends to 0, but if it doesn't, then you finish the question before you start it. Then the next step, we shall call the first step, apply 5 spots tests. You don't have to apply all 5 of them, right? But you can apply 5 spot tests to the series of absolute values. If it's absolutely converging, we are done. Because we proved that when a series absolutely converges, it converges. And lastly, we use Dirichlet test or Leibniz. It's not how you write Leibniz at all. Leibniz. Leibniz. Still false. That's okay. Leibniz, that's the difference. I was wait, yeah, I was close yet far. L-E-I Leibniz, and without the
Sorry, the 0 is only if it's positive.
wait, just no, the 0 is always. When a series converge, AN goes to 0, always. It's not just for positive, or Leibniz sets, or a direct summation calculation of the PSS, like in telescopic series. Okay. So most of the heavy lifting happens in step number 1. That's most of the work. But you do need to have a good understanding of these 3 steps, which are used in general. Any questions so far? Yes, Sammy.
Practically. like,
This is the most practical.
The only time to is then why we add rather
Hmm.
absolutely conversion.
I must say that's the absolute opposite of practically. But yeah. Yes, no, I agree. First of all, like you see, yeah. No, but you are interested in the theory, not the practice in this question, because practically what we say. But theoretically, first of all, as you see in practice, it's powerful because absolutely convergence make sure promises convergence. So you can use the Spock test. You have much less less types, a number of tests in general series. So you have many tests for a positive series. There are a few more that I didn't teach. So that's one thing. It's easier to check whether the absolute value is convergent than the original series. But more than that, and that's kind of interesting, and I will answer it with the following example. An interesting example. We have seen that the sequence of n equals 1 to infinity of minus 1 to the n over n is converging, but not absolutely. Agreed? It's conditionally converging. Minus 1 plus a half minus a third plus a quarter and so forth equals some number. I think I told you before it's minus log of 2. I said I'll write log in this course. It's minus log and 2. Later. It doesn't really matter. It converges some number. Okay? Now, what do you think about minus 1 minus third plus half minus a fifth minus a seventh, plus a quarter, and so forth? What is the connection between that and this? So it's just different order. That is just a different reordering of the same sum. Agreed? Right series. What do you think about the convergence? So let me try. I won't show you the whole thing, but I will try to give you an idea of what's happening here. If you take 1 minus 1 over 2n plus 1, and you add 1 over 2n plus 3, so this couple is like that couple over here. Oh, sorry. Right, I coupled each two consecutive negative ones together. Okay, so far? Wait, it's not all. I just took this couple here. Okay? That equals to minus, and then we get, what do we get here? Not sure about my point here. Just no, I think it doesn't work as.
No, if it's positive or negative, it works. Or negative and positive.
Wait a second. I'll still do it. I didn't prepare a full proof for what I'm about to show you. I think it will be fine enough. If I add them both, then we'll have 4n plus 4 over 2n plus 1 times 2n plus 3. Really does not show what I wish to show.
The previous one,
the one that's positive or negative is one over n times n plus one, that's why it works, right?
Do you know where I'm getting at?
I think like the previous one works because it's telescopic, right? And this one.
No, this is not telescopic, it's Dirichlet. That's the point. We didn't even prove Dirichlet yet. My point is, and I'm failing to show you with ease that it works. I might switch the example for something easier. I remembered that this should be easy enough. But the point is that this way I doubled the negative numbers in a sense, right? And because there are so-called more negative numbers, even though they're not, and it will cause it to go to negative infinity. So I'm pretty sure that it's true, first of all. I'm not sure for sure, but I think it's true. But I thought it will be much easier to prove, and it was not. So let me give you another example. I will just say, does the sum stay the same? It's unclear, okay? Let me switch it for an easier example when I can absolutely show you the sum is different. Take another example. And the series will be 1 minus 1 plus half minus half plus a third minus a third and so forth. What is the infinite sum of that series? 0. Why? Because the partial sum is either 0 or 1 over n. And in each case, it goes to n. But what will happen if I change the ordering a bit? And I hope it will work this time. Let's do 1 plus half minus 1, that's a half, right? Plus a third plus a quarter. Also quite hard to do. Let me think about it for a second, sorry. Oh, I remember. I have a good example. Okay. Plus half plus minus half. And then plus third minus third 3 times. And so forth. Okay, I think this is fine. So the other one is 0, like I said. But now I can do something like that. 1 plus half plus half. How much is that? 2, right? Minus 1. How much did I get here? 1, right? What is the next element I should add? A third. And what can I need to do it with powers of 2, I think. Whatever. I think this is good enough to understand. Minus a half, minus a half. Or just minus half 1 time. Enough. Okay, minus a half. This is still altogether positive. Let's always stick to the 1. And that's it. Okay, finally, I think now I'm pleased. I added 1, then a couple of halves, that's 2, and then I subtracted the first 1. So I have at least 1. Agreed? Then I add the next 3 elements. Third, and third. Altogether is 1. So now I have 2 again, right? Now I can subtract the next number. Which is the next number that I should subtract? halves, just one of them. Just one of them. And then I will add the 4 quarters. That's another one. And subtract the next half and so forth. Meaning I'm adding up so many. I think that just doubling it's not enough to cause what I'm doing here. But here I add so many. Yeah, I was actually whatever. Here I add so many positive numbers together, and the negative numbers appear every now and again, becoming more and more scarce. They always appear at some point, right? We never forget about them. But this is unequivocally larger than 1. Okay, meaning that the reordering changed the sum. Okay. And now, Sammy, why is that an answer to your question? The theorem, which I will not prove, if a sum absolutely, a series, sorry, if a series absolutely converge, reordering its elements does not change its sum. And when the series is conditionally converging, Riemann theorem says, and there is proof on the wiki for whoever wishes to see it, says that you can reorder it to converge to whatever you want. I can reorder it to converge to pi, and I can reorder it to converge to e, whatever I want, okay? So if anyone is curious about it, you can look, but that's the main thing. Absolute convergence says reordering does not hurt us. And why is it actually important? When you learn probability, sometimes there will be, and I showed you one example of it, there will be infinite probabilities that you wish to sum. And then you might fear that if you chose the wrong order, you get a different answer. No, because it's a positive series, it's absolutely converging, the order does not matter. But if it's conditionally converging, the order really matters. Surprising, but that's true. Okay. And here I think the order will change the convergence, but not necessarily whether it's converging at all. Here, I think that I chose correctly, it will diverge to infinity. And I don't wish to prove it, but I'm pretty sure that because each time I'm adding 1 minus something that tends to 0. So I am adding 1 minus 1 over n. So it's like adding 1, basically. I think that goes to infinity, but I didn't prepare it because I didn't wish to get into it, okay? But that's the main difference between absolutely convergence and regular convergence. Any questions so far? So let's proof of Dirichlet theorem. So I'll remind you of the assumptions. We are given an that tends to 0 and decreasing will be important in the proof. And we have the n with the partial sum sequence Sn, which is B1 until Bn. And such that Sn is bounded, smaller than some number in the absolute value. We need to prove that the sigma, the series from 1 to infinity of A and Bn converge. And I just restated the theorems and given a couple of things names which I will use. Okay. And I warn you ahead, the proof uses a trick. This is the kind of proofs that is hard to think about by yourselves. Dirichlet probably thought about it. Consider or write dn for the partial sum of the series we are looking for. We need to prove that dn converge to a finite limit. Okay, that's the partial sum sequence of the series where we actually care about. If we took the absolute values, it doesn't have to be converging. It could be that the sum of an is too large. The convergence appears because it's sometimes positive and it's sometimes negative. And we have to be able to take that into account some way. Agreed? So now for the trick. dn is equal to that. But we can write also, instead of writing b1, we can say b1, well, sorry, b1 has to stay b1. Next one. Instead of b2, we can write s2 minus s1. Agreed? Right? S is the sum, partial sums of the bn's. So s2 is b1 plus b2. If I take out, I can call that one s1. Okay? But this is s2 minus s1. What will be the next element? A3 times S3 minus S2. And lastly, an times Sn minus Sn minus 1. Agreed? It's not clear why would we do that. You will see in a bit. But I hope it's clear that it's true. Okay, we decided to use Sn instead of the Bn. I will tell you why this also makes sense, because all the assumptions we have are about Sn, not the Bn itself. I didn't tell you anything about the sequence Bn. I told you that its partial sum sequence is bounded. So it makes sense to replace Bn by an equivalent expression by Sn. Yes, Thomas.
We said that if sequence is associated, the series converges, I think, right?
Yes. Yes. Okay. And it's a good note because I forgot to say that. Now, let's look at dm minus dn, and what do we get here? We get the sum of an times, I'm starting from the end to start, Sn minus 1 plus an minus 1 times Sn minus 1 minus Sn minus 2 plus and so forth until the last element is one before that, plus an plus 1 times Sn plus 1. Sorry, Sorry. I should have said ended with M, not with N. Sorry. That's M, 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 and the end is with N. So that's N plus 1, Sn plus 1 minus Sn. Okay? So now what can we say about that? We take out the S's as common factors. We get AMSM, that's not very interesting, but the next one is AM minus 1 minus AM times SM minus 1. Okay, you see why? Because SM minus 1 appears twice, once here and once here. I take it out as a common factor, and I'm left with AM minus 1 minus AM. Okay? Plus, the next element would be AM minus 2 minus AM minus 1 times SM minus 2, and so forth until the last one. Let's add another one before here, it will help. That's AM plus 2 times Sn plus 2 minus Sn plus 1. So the last pair is A n plus 1 minus A n plus 2 times S n minus n plus 1 and minus A n plus 1 minus A times S. Okay, so there are a couple of expressions that appears only once. Sm appear only once, and Sn appears only once, but all the rest appears in pairs and opens up like that. Agreed? Now, this, what is its limit if I just take m to infinity? Just this expression. 0. Why? Because this is bounded and an tends to 0. Agreed? This also tends to 0. To be honest, we don't care about these two. All the rest is the main thing. So what can I do about the rest? Now we do the nice trick of it all. If I take in absolute values, what we have here, it's smaller or equal than AM minus 1 minus AM times S m minus 1 plus the last one is A n plus 1 minus A n plus 2 times S n plus 1. Yes, yeah, it's the triangle inequality. Yes. I just use that in the right place. What can you say about the absolute values of all of the S's? Sn minus 1, Sn plus 1. What can you say about all of them?
Bigger than bigger or equal than Sn, whatever it is.
No. It's smaller than m. because the partial sum sequence is bounded. So all of these are bounded by the same m. So that is smaller or equal to am minus 1 minus am plus, sorry, I forgot the big M, I put it outside, plus the last pair, which is this one. Once we added the absolute values, then all of the SNs, we can take them out. But the ingenious of it all is what happens here. The absolute values hurt me because I have a sum of an indeterminate amount of elements, and I fear that I can't say anything about this sum, but I'll be wrong. Can any of you remember what are the assumptions of the test? I'll go up and remind you. We said that Sn, the partial sum sequence of Bn, is bounded, and we use that. What else do we have here for assumption? An tends to 0. We actually use that as well, and we'll use it again. What else? It's decreasing. What does it tell you that it's decreasing? What is the sign of this expression? Negative, because it's decreasing. It's the next element. Wait. It's the next element. No, it's the previous. No, it is positive. Sorry, it is. It's the former element minus the next. It's always positive. So what happens to the absolute values? Okay. That's the whole thing of the whole trick here. It allowed me to add absolute values and then have it vanish. Okay? That's, I will tell you, to be honest, that's something I don't remember by heart. I looked it up just before class. It is written in my wiki, right? But I didn't invent it. I don't usually remember it. Because it's such a nice, surprising trick. Second, okay, you wish to have only this. This is larger than 0. This is larger than 0. And if we delete all the absolute values, if we remove all the absolute values, what are we left with? Am minus 1 minus am plus, what is the next pair? M plus a minus 2, sorry, plus am minus 1, and so forth. The last pair is a
minus 2.
and the last one is n plus 1 minus n plus 2. And what happens with everything here?
Sorry, I don't know why you add.
No, that was a mistake. That's 3.
3 and then it's 9.
3 or 1. Wait a second. Am minus 1 minus am minus 2 minus am minus 1 of 3, and it's minus, yes. Wait, minus, yes. Yes, sorry. So it's a telescopic sum, right? A minus 1 cancels out with am minus 1, and we are left with only m times am and
Negative am?
right? Negative am. And I didn't make sure who are we left with. Who is the last pair? Let me think about it for a second. I didn't write it here. Before it's am plus 3 minus n plus 2. So I think I think you'll have a n plus 1 will remain. I didn't make sure who of them, and I think another one which is negative and not canceling out. That's it. I'm not completely sure, to be honest. Let me make sure if that is written. I didn't think that one through. Doesn't really matter because we are left with 2 and not an indeterminate amount, but in any case, if it's written, I could be wrote it a bit differently here. I wrote it a bit differently here. Let me think about it for a second. Because I left with, okay. I wrote the example a bit different. So I'll just write here, I put in a question mark. It doesn't really matter. I can prove by induction and do a couple of instances to make sure, but it's about 2 terms. And in any case, the point is the distance to 0, because it's just the sum of 2 elements. This tends to 0, and thus, and therefore, dm minus dn is smaller in absolute value than some expression that tends to 0, therefore dn is Cauchy and converge. I'm just not sure about the last elements that are left here. I didn't prepare that one well enough ahead. But the main thing is this is telescopic. Almost everything cancels out. And you are left with the start of the series and the sequence and the end. These are 2 or 3 elements that goes to 0. Therefore, it's as small as I like from than any epsilon I would like. Okay, so that's the main thing about the Dirichlet test. And for the end of the class, I will just write a Leibniz test. Say CI. Leibniz test. If an goes to 0 and decreasing, then the sum from n equals 1 to infinity of -1 to the n converge. And the proof, it's a short one, immediate from Dirichlet. It's just a specific example. Instead of Bn in general, I take the sequence -1 to the power of n, whose partial sum sequence is bounded. Okay? We usually use Leibniz test, but it's a very easy consequence of the general Dirichlet test. So that's enough for today. See you guys on Tuesday. And then we start functions. We finish series. Functions.
No, not me.
I won't be, or.
Computer science,